Listen, you need to stop and start paying attention. Everybody look up here. Stop working on whatever you're working on. We're going to do our last notes of new material for the whole year. Crazy, huh? First, we're going to talk, we have two things to cover. Binary search and merge sort. So, binary search. So far in terms of searching, we've learned the linear search, right? Start at one end and go through in order and look for something. I mean, you could start at the beginning or the end, but you're going to go in a line, like next. It's called a linear search because it goes in a straight line sequentially. All right, a binary search can be much quicker, but you can only use it if the data is sorted. But if you happen to have a sorted list, binary search is exponentially faster than a linear search. So here's how a binary search works. You start by checking the middle element and see if it's your thing. And if it is, you won. You got it on the first try. But if it's not, now because the list is sorted, you know that it's either above you or below you. So at that point, you rearrange it so that the middle is the new, let's say it was below you. Then the middle is now the high range, and you still have the low end of your list. And you pick a new middle, which is between those two. And so you keep moving, which is the top and the bottom, and you're getting rid of half of the possible elements every time. So if you had 32 elements, the maximum number of times you'd have to run this search is 5, because 2 to the 5th is 32. And if you had 1,000 elements, the maximum number of guesses until you got it right would be 10, because 2 to the 10th is 1024. So, and if you had 1,000 elements, it might take 1,000 checks if you were doing a linear search, right? What if the thing you were looking for was at the very end and you start at the beginning and you're like, is this it? Is this it? Is this it? 1,000 times. And it's at the very end. Whereas if it's a sorted list, a binary search is fantastic. And here's an example. So we're going to look in this array for the number 7. So it would help you to definitely pay attention. You want to have a low value. You're going to have to code this at some point. You want a low value and a high value. Low index and high index. This thing has 9 elements in it. So the low index is 0. High index is 8. And you want to find the middle. So 0 plus 8 divided by 2 is 4. So we check the thing at index 4. Hey, is this a 7? Nope. So, and we know that what we're looking for is to the left of that 9. Like we're checking this value. Oh, that's not 7, but we know what we're looking for is less than that. So we can throw away the whole right side. We don't have to look there anymore. That's how we get rid of half each time. So now the low is still 0, but the high becomes 1 less than the center. Like we know it's not the center. We can exclude that one. So our high, the low is now 0. The high is 3. 0 plus 3 divided by 2 is 1. So we check that one. Remember, we're doing integer math. We check that one. Is that 7? Nope. So then we're going to move the low end up to the 1. And so I said up to the 1. Oh no, the middle. We move it off the middle. So the low end gets moved to 2. So the low is 2, the high is 3. We add them together, divide by 2, we get 2. Is that 7? Nope. So then we're going to add 1 to the low, and then finally the low and the high and the middle are all index 3, and we find our thing. So that was like the maximum number of searches probably for a 9 element array. Yes.
Why would you use that instead of a linear search? Because I feel like they kind of do the same thing, but just a lot.
Well, a linear search, you missed it. If you have it for a thing this long, sure, a linear search very quick. But if there were 1 million entries, a linear search might have to search through 1 million entries before it found it at the end. And it would only take 15 checks. if it was a binary search, gets rid of half of them every time. So after one check, it'd be only 500,000, and then 250,000, and then 125,000, which sounds like a lot, but you're getting rid of half of the possible places every turn. Another example is, let's say you were playing a number guessing game and somebody had to guess 1 through 10. Yeah, linear search is fine. You could start at 1, 2, 3, but if the user had, if the number you were looking for was 10, it would take you 10 guesses. Whereas if you did this, it would only take 4 guesses max, because you get rid of half the possibilities every turn. So yeah. You got to remember with Java, when it can't find something, whatever your code has to return a -1. -1 means couldn't find it. Remember, we do index of something, and if it doesn't find it, it just says -1. And remember, this algorithm only works if the data is sorted. So here's another run. This array has 8 elements. So the length is 8. So the low is 0, and the high is 7. So 0 and 7. We're going to find the middle. Remember, the algorithm is find the middle. So 0 plus 7 divided by 2 is 3. So we check that one. And we're looking for the number 10. So because 10 is greater than 7, we're going to keep the right half. So our new low is index 4, and our high stayed the same. So then we got 4 and 7. Add them together, we get 11 divided by 2 gives us 5. 5's to yes.
I was just wondering, would this code still work if like the low, high, and middle were doubles instead of ints?
No, because if you're trying to access an array, it'll work with double values in the array, but the index values can't be doubles.
Okay.
Yeah, no, so it won't. No, it won't. So here we're looking for a 10. The right-hand side is too big. We lop it off, and so now I think we're going to be at 9 and 9 and 9. Low, high, and middle are 9. 9 is not 10. And so then it tries to, it figures out if it goes any farther, it overlaps. The low and the high kind of cross over each other. And so we bail and return a -1. So binary search can be implemented using recursion or with regular loops. Today we're going to look at a recursive implementation. You won't be asked to code one of these on the AP exam. You might be asked, you'll see when we do more of these, you might be asked, like, how many times does line 7 execute in the following code when we search this array for this data? And then you'd have to be able to trace it. So, but let's look. Here is, and I'll give this to you in the slide deck. This is a recursive binary search. And what happens is you call this function or this method with the array that you're searching, and you send over the low and the high and the thing you're looking for. All right, so check it out. I put this in here. Like if you wanted to copy this and play with it, you could copy the code, and it'll print a period every time it gets to this spot. It's kind of fun to see. Like, oh look, it called itself 12 times or something. But if here's kind of how it exits. This would be the base case. If low is greater than high, that means you didn't find it. You start with a low and a high, and if they go towards the center and then the low gets bigger than the high, that means you couldn't find it. So we return -1, it wasn't found. Otherwise, we find the middle. The middle is the low plus high divided by 2. And then we check, did we find it? If target is equal to the middle item of the array, then we return the index where it got found. Otherwise, hey, the target is below the middle. We have a new low, a new high. See, it's almost the same call. We send the array. It's the same low value, but the high value becomes the middle -1. And if it was on the right side of the middle, the low value becomes the middle +1. This is actually really clean, and if you trace this, you ought to be able to understand this. I understand if it's a little hard to see from here, but so again, what makes this so fast and so great is it throws away half the index values, half the elements don't have to ever be searched again. Each time you've tried it, you've gotten rid of half. So, and if you're doing a linear search, it might take 1,000 individual checks to search 1,000 item list, whereas it only takes up to 10 if you're doing this one. Of course, it has to be sorted. So, but hey, if you had a sorted list, this is awesome. Speaking of sorting, we have a third sort method. Do you remember we had insertion sort and selection sort? We learned those in the, I think it was the array list unit. This one uses recursion. And what it does is it splits an array into smaller and smaller pieces. And then it sorts those pieces and puts it all back together again in the right order. And yes, it's basically magic. I can't really explain it. And on the AP test, you don't have to code it, but you may be asked to trace it, or, this would only be on like a multiple choice question. But I wanted to show you this link, which covers the merge sort. So if we had 4 elements in an array, the merge sort breaks it in half, and you have this little mini array, and then it figures out, and it breaks it in half. It calls itself again, and then it says, oh, okay, well, these I'm going to change the order, put them back together into a little array of 2, and then it took the high end, the 43, and the 10, and it made that a little array, and it sorted that stuff. And then it comes back here. It's got these 2 things, and it merges all them into the right. It puts them all back together in the right order. It's just freaking magic. There's it walks you through it all if you want to look at it. And then here's actual code, and have fun with that. Anyway, I don't think I could code this myself. And you don't have to code it. As I said, on the AP test, you won't have to code it, but you may be asked to trace it, and they would give you code. And then, and we'll talk strategy on the AP exam. Like when you're going through, you have 40 multiple choice questions and 90 minutes to do it. So it's 2.25 minutes per question. So if you run into a merge sort question and it seems really complicated, you could always put that off and work on it later after you've gone through all the other ones. And then if you ran out of time, you could always just guess, because then you have a 1 in 5 chance of getting it right, even if you guess. And you shouldn't burn 10 minutes on a merge sort question on the AP test if you don't understand what's going on. Just go to the next question and then come back. So you'll have access to all of that. And I'm going to start saying this every day. The AP test is Wednesday, May 8th at noon.